recording going, of course. So I added something to the webpage, and I forgot to mention it last time. I added right here on last week's class a program that I had written. I suddenly remembered it. I wrote it several years ago. How to simulate data that have linear and quadratic trends in them. So this is a SAS script that you can play with. There are just a few features of it at the beginning that you can change in terms of what the fixed effects are and what the variances are, and then you can run the program and it will spit out a plot that generates trajectories. So if anyone is curious as to how to simulate data or how these things sort of work under the hood, this is one way hopefully that might be helpful to you in learning how to do that. I only know how to program in SAS. So if you're, oh, everyone's frozen. That means I'm frozen. Are we back?
Lisa, you just cut out for about 2 minutes.
2 minutes?
Well, maybe not 2 minutes.
Yeah. Am I back now?
Wow.
Okay. All right. Yeah, I don't know what the deal is. I'm sorry. I've already shut down every app that I possibly can that's connecting to the internet, so we'll make it work. But what was I rambling about when you lost me? SAS program could help. Yeah. So I have a program up on the website that you can play with. I wrote it for students to play with, to sort of visualize what happens when you have linear versus quadratic trends in your data, but it could also be useful for those of you who are learning how to simulate data, a little bit of a preview of what goes under the hood. What I was going to say is that SAS is the only program that I have learned how to simulate data in, but all of the programs can do it. So I was just, in R, for instance, I know there's a ton of resources online. In Stata, people have figured out how to do this. So I can help you track down resources if this is something you're interested in, but I can only personally provide resources in SAS. So I have that there. And the other thing I wanted to point out is that I have updated the R code for one of the models from example 6. So as usual, in putting together your homework, I realized that the examples that I have did not get everything in R that you need to answer all the questions, and so I had to go back and add a few things. So your next homework is available. It is due in 2 weeks from yesterday, and you should be able to do 2/3 of it, 3/4 of it or so right now, and then hopefully after today you'll be able to finish the rest. But if you're planning on using R for it, make sure that you read the instructions carefully to the homework, because you have to use a different R package for each section. I'm just the messenger, but that's what happens, right? And so, for instance, I figured out that every other package ran one of the models just fine, but R's Elmer threw a warning that resulted in incorrect parameter estimates for the variances, but LME did it just fine. So it's a series of trials and errors with respect to that. So just make sure that you're paying attention to which routine you should be using in R for each section according to the instructions. So, all right. Any questions, comments, any big picture stuff that we need to go over before we dive back into the little picture stuff? No, we're all raring to go, caffeinated, fed. Raring is a relative term, isn't it? Like, well, I'm awake, if that's what you mean by raring to go. All right, what am I looking at? Oh yeah, quadratics. That's what we get to start talking about here. So we've spent the past several classes reviewing the steps in terms of how to approach a longitudinal analysis. What would your baseline models be? We talked about the biggest answer key baseline, the idea of saturated means as the answer key for what the model is trying to predict with its fixed effects of time, and unstructured variances as what the model for the variance is trying to recover in terms of the variances and covariances across occasions. That's one end of the baseline. The other being empty means, random intercept only is the simplest version that you would entertain, and then some possibilities in between the two. We were playing with these example data. So this is slide 5 of lecture 6 that I'm reviewing here. So we have 6 occasions of response times. The means for those 6 occasions follow this black line here. So the rest of this set of examples and this lecture is presenting you with some alternatives for how one might describe this type of what I would call a bendy line. It's not a straight line, it's bendy. And there's lots of ways to operationalize bendy. The first one that we're going to do is quadratics. The second one is piecewise linear slopes, then truly nonlinear models, and then approximations of that using log transform time. So we're trying to match this black line today. That's what we're trying to do on the mean side. At the same time, on the variance side, we're trying to match this black line. So this is slide 8. This is what the estimated total variance is at each occasion from an unstructured variance model. So it looks like variability decreases as people become more and more familiar with this task. So we're looking at changes in response time across 6 practice sessions. And so far we looked at a linear model, which did not fit the average trajectory very well, and a random linear extension to it, which made the model better, but probably isn't going to be sufficient either. So now it's time to consider some alternatives to just straight up linear. So that's where we were going to pick up. So any questions before we dive into some new stuff? All right, the good news is, how many of you were in 6242 with me? I'm looking at the faces here. I'm guessing like half of you maybe at this point. Well, if you were in 6242 with me, you already know how to do what I'm about to talk about. We did quadratics in that class for this reason, because nonlinear effects of quantitative predictors in general is something that you should learn how to model. So it shows up in the context of time as a quantitative predictor specifically, but what I'm about to tell you about applies to quantitative predictors in general. They may not have linear effects. They may have curvilinear effects, and so it's useful to know some common strategies by which to describe them. So we're talking about polynomials then. Slide 11 on lecture 6 is where we're talking with. So this is probably by far the most common approach to modeling nonlinear change over time. It's the most common because it's the easiest. It works. Every software package will give this to you. It's still a linear model because it obeys the language of slope times variable plus slope times variable, which means you can use any standard package to estimate these models. But from a theoretical standpoint, they are less useful. So we'll see pictures as to why that might be. But the idea here is that we're going to include as distinct predictors time squared, time cubed, time to the 4th, right? That's the type of idea here. So if I have time in the model as a predictor, that is a linear slope for the effect of time, specifically. A linear slope means that change is predicted to occur equally all the way across units of time. So the effect of a 1 unit change in time happens equally across all of the occasions. Linear change. A constant rate of change. If I add to the model a new predictor that is time squared, then what I am saying is that there is a change in the rate of change. So the rate of change slows up, slows down, or speeds up. I don't know what slows up would mean, but I suppose that's possible. So in physics terminology, people refer to this as acceleration or deceleration. So like if you're driving your car and you put your car on cruise control, right? Like that's like linear, like you're going along at the same speed, your car is maintaining that speed. But if you need to hurry up and pass a big truck, you put your foot on the accelerator, accelerate it, and it increases your speed so that you can pass. So adding time squared as a new predictor then allows for an acceleration or a deceleration of the change. It is a constant change in the amount of change. If you add time to the 3rd power, time cubed. That's what's known as a cubic model. Then you are saying that there is a change in how the rate of change changes. What's known as, in physics terms, as either a jerk, a surge, or a jolt. And I like jerk the best because it's like, who would put time cubed in their model? What a jerk. No, it's a cubic trend. In practice, you can have higher order trajectories. You could put time to the fourth or time to the fifth. I have never seen anything like that be even remotely useful or interpretable past time cubed. I have seen a cubic that actually made sense, but beyond that, nope. So in general, the rule as to how many of these polynomial trends for change over time you can include is based on the number of occasions. So its number of occasions minus 1 is how many fixed slopes related to time you can put in the model. It's minus 1 because you always have an intercept. So if I have 3 occasions, then I can put in a fixed intercept, time to the first power, linear time, and time squared. That's 3 fixed effects, will perfectly recreate my 3 means. If I have 4 occasions, I can pick up time to the third power, and so then I'll have intercept, time, time squared, time cubed, and I'll have 4 parameters that perfectly recreate the 4 means. So there's not really a savings or a prediction that happens if you fully saturate your model with as many polynomials. It would be the same thing as a saturated means model at that point. So the objective would be to try and use fewer than all possible in order to describe the trajectory. In unbalanced data, you can get away with more because then the mean trajectory that you're fitting has more potential means in it. So like if you had, time 1, 2, 3, 4, and the next person has time, 1.5, 2.5, 3.5. Even though each person only contributes 4 occasions, now there's like 8 different points on the line that you could recover, which means you could have higher order polynomials. But be very careful in trying to do that in practice. So in general, number of occasions minus 1 is a good guideline for the most that you can have in here. Now, what to do with the quadratic slope? It is my great wish that none of you ever writes something like this. Well, quadratics are too hard to interpret, or it's complicated. No, it's not complicated. This is what I want you to remember. Twice the quadratic is how linear change changes per unit time. Twice. That's the magic that makes it complicated, the number 2. Another way of saying that is that the quadratic slope coefficient that is provided as your fixed effect is half the rate of acceleration or deceleration. So you have to multiply it by 2 to get to the full rate of acceleration or deceleration. And I can explain this to you, why it's twice, 3 different ways. So here's way number 1 for those of you who might remember calculus. If you don't remember calculus, feel free to ignore me for the next minute or 2. So what I'm talking about is taking the first derivative of a smooth continuous function and then taking the second derivative of the same function. The rules for doing that, like if I were to take the derivative with respect to time, let's say I have a function that looks like this. I have an intercept of 50, I have a linear slope for the effective time of 4, and I have a quadratic slope that's say 0.3. For the first derivative with respect to time, which would give me the slope at time t, so that the term for that is instantaneous slope at that occasion, then here's what the equation would be. The squared comes down in front to multiply it by 2. The second derivative is 2 times the quadratic. So it gets multiplied by 2. So twice the quadratic is how the linear slope changes per unit time. If you don't like this, maybe you'll like it this way. So the second way that I know how to explain this is in the context of what normally happens when you talk about interaction terms. So if I had a model that looks like this, this is just a regular old regression model. I've got beta 0 as my intercept, beta 1 is a slope of x, beta 2 is a slope of z, and I have beta 3 as the interaction term. in this interaction model, beta 3 does two things simultaneously. It makes the effect of x change as a function of z, and it makes the effect of z change as a function of x. It plays two roles because it moderates each of the main effects as a function of the other predictor. Well, if I try to recast this linear regression model as a longitudinal model, it's like I'm missing the other main effect, because time squared is an interaction term. It's time multiplied by time. So because there's no second main effect that beta 3 would say changes as a function of the other variable, it has to change the linear slope twice. So twice the quadratic coefficient is how the linear slope changes per unit time. And if you don't like that explanation either, then I have to go to the third one, which is because I said so, right? At some point, and as a parent, you will say that, and you'll be like, oh my God, I can't believe I just turned into my mother. But it will happen. Because I said so, that's why. No, you can't take your mattress and slide it down the stairs. Actual request, by the way, of my stepdaughter when she was about 5. She wanted to take her mattress and slide it down the stairs. Reasonable request, denied. So twice the quadratic is how the linear slope changes. I've got some pictures that hopefully will make it a little bit better. So I have 4 examples of how a quadratic slope would modify a linear slope. And it boils down to the same 4 types of interactions that you've heard me say probably before at some point in another class. There's only 4 kinds of interactions, right? An interaction term takes its main effect slopes and makes them more positive, more negative, or less negative. That's it. There's only 4 possibilities. So the same thing happens in this context in talking about how the quadratic slope changes the linear slope as time passes. So here's a function, top left here on slide 14, where I have a linear slope that is positive 4, and the quadratic slope, so the coefficient that would multiply time squared, is a positive 0.3. So note that time starts at 0 here on the x-axis. Y is some hypothetical outcome. So just as we talk about once you add predictors, the intercept is the expected outcome when time equals 0, the same thing is true of the linear slope. So in these pictures, 4 is the change in y per unit time at time 0 specifically. It is the slope of the line that is tangent to the curve at that point, which is what these little dotted lines is trying to convey here. So at this occasion, the slope for change over time is 4. As time goes on, the quadratic slope kicks in, and for every additional change in 1 unit time, so going from 0 to 1, 1 to 2, 2 to 3, the linear slope that was 4 becomes more positive by twice the quadratic coefficient. So the quadratic coefficient in this example is a positive 3, or 0.3, excuse me, 0.3 times 2 gives me the 0.6 change between each of these increments. So the linear slope that is 4 becomes more positive by twice the quadratic each increment of time. So the end result is a positive slope that increases. So the rate of change accelerates in this picture as time goes on. So think like the growth of bacteria on a sponge, or COVID cases after spring break. You know, fun examples like that. Acceleration is the idea here. So this function is showing growth over time, but the rate of growth is increasing. The rate of growth is twice the quadratic, is how much it increases per unit time. So that's why it's 0.6 as what the slope difference is between each of these subsequent occasions. Okay, with me so far? So this is a more positive line. Over on the top right, this is a less positive. So now the signs are opposite. I have a positive linear slope at 4 at time 0, but now the quadratic coefficient is a negative 0.3. So the quadratic is acting in opposition. It slows it down. So the way I would describe this trajectory is that there is a positive rate of change of 4 at time 0. That positive rate of change becomes less positive by twice the quadratic every unit time. So it's slowing down. And what does the model say is going to happen after time 5? Where's this function heading? Yeah, this is a gesture question, or you could make a drawing. Yeah, it's heading over the top of the mountain and it's eventually come back down the other side. So the other half of this picture is, let's see here. This one, is it? No, it's this one. So it's like this, where it leaves off here is here, and it's picking up and heading down the hill. Likewise, this top picture right here, the top left, the other half of it is the bottom left. So there's only really two kinds of quadratics, either the u goes up or the u goes down. The question is, which side of the u are you on? I call this top left increasing positive because during the range of time that's observed, there is positive change. People are going up. The rate of upness is increasing. Over here, because it starts out positive, I would call this positive change that slows down. It doesn't exactly hit to the point where it turns negative within the span of these data. So this is a declining rate of change. But what I said a few minutes ago about these models being sort of theoretically not the best choice is a consequence of what goes up must come down. So if you think about, say, this top right trend as achievement growth in students. As students, when they start school, they have a steep learning curve. As you may hit close to, say, a test ceiling, right? You can't go up on average very much longer once you hit the ceiling. But what the model says is what should happen after they get to the ceiling is that they should go back down the other side. How often is it the case that what you've learned goes away? Yeah, possibly over summer vacation. Possibly if you stop using the material and then you come back 6 months later, right? But that's a different problem because then it's more like a function that goes up and drops down the next time it's tested. It doesn't gradually get worse again. So these models work well for limited ranges of time to simply capture nonlinear change. They don't work well in a forecasting sort of what is the theoretical mechanism kind of way, because it's unrealistic to expect that things that were decreasing would start increasing again or vice versa. So these are both positive trends that either speed up or slow down in the top two ones here. All right, how are we doing so far? Okay enough? Okay, so then the bottom one, these are negative trends that either slow down or speed up. So on the bottom left, this is a negative trend. So the slope at time 0 is -4. There is a positive quadratic coefficient in this picture that is making my negative rate of change less negative. So there is decline, the rate of decline is slowing down. So this is the type of trend that we have in our data. We have response time improvements as time goes on, but the rate at which people are improving starts to slow down. So decelerating change in this case. And then decline that speeds up is over here on the right. So hopefully if everybody does get vaccinated like they're saying, then this will be the COVID cases, right? Decline in COVID cases that accelerates and continues down to flatten the curve. Remember that? Wasn't that cute? That's what we were saying this time a year ago. This is the curve. That's what we're talking about. So the question then that you have to ask yourself in faced with any data set is, which of the four do I have here? You either have a linear slope that's more positive, a linear slope that's more negative, a negative linear slope that's less negative, or a negative linear slope that's more negative. It's one of the four. So then the trick is making sure that you understand what is conditional on what in talking about the resulting model parameters. And there is a very much algorithmic, orderly fashion to talking about these things too. That's the good news on these front. So question, accelerating and decelerating would be more like the absolute value of the change, and the direction of the function is described as negative or positive. So good question. So I recognize that there's really only two kinds of quadratic functions, in the sense that the u is either positive or upside down. So it either looks like a happy face or a frowny face. My focus is on which section of the u that you're on, and thus what the verbal description of change would be as a consequence of the interaction of which type of linear you have and which type of quadratic. So this negative quadratic, for instance, right here, in this top right picture, is slowing down a rate of growth. So I would say that there is growth that is slowing down over time. A negative quadratic down here in the bottom right is taking decline and enhancing it. So here I would call this an acceleration of decline, which is a different phenomenon than a slowing down of growth, even though these are part of the same sort of mathematical shape. So it's about the substantive interpretation of how you describe what the quadratic is doing to your model in the range of time in which you have the data to fit the curve to. Okay. All right. So interpreting parameters then. So if we start with just an empty model in terms of the model for the means, fixed intercept only, that's the predicted mean at any occasion. So we would start with the flat line. If we add a fixed linear time slope, so just adding a predictor for time, what you might call a main effect of time, I would call a linear time slope, emphasizing that the interpretation of the function is that it is a linear slope of time specifically. In that case, the intercept is then conditional. The intercept becomes the predicted mean given by the line wherever time zero is. That's the new intercept. So the intercept from the empty model is not the same intercept from the second model, because they mean different things. So they will be different numbers because they are representing different quantities. If the fixed linear time slope, though, if that's the highest order term, then it is unconditional. It is the rate of change per unit time in the outcome, period. And it doesn't matter where time zero is, because a linear function says the change is the same all the way down the line. If I then add a fixed quadratic time slope to the model, the fixed intercept stays the same conceptually. It is still the predicted outcome at time zero, but now it's predicted by a bendy line, not a straight line. So the prediction should be different, because the function at time that time zero is going through is going to be a different function. But conceptually, it's still the same idea. The switch is what fixed linear time means. It is not the same linear time trend as it was in the previous model. It too is conditional. So once you have time squared in the model, the coefficient for just linear time is the linear time trend at time zero specifically. And so then the quadratic comes along and either slows it up or speeds it down. Okay, apparently we're going to have one of these days again. You know what I meant, right? Make it go more upper or more downer. So the trick then is just making sure that you know what these things mean, which are relative to time zero and which aren't. If the quadratic trend is the highest order term in the model, then it is constant. So it is a constant rate of acceleration or deceleration. Can you guess what would happen if I added cubic time, time to the third power? What would happen to my fixed quadratic time if I had cubic time in addition to it? At time 0, exactly. It becomes conditional as well. And then it is the rate of acceleration at that point, because a cubic model predicts the rate of acceleration to change across time. Yep. So these things are all hierarchical. That means that you have to keep all of the lower order terms for the higher order terms to be interpreted correctly. So time squared is only a quadratic if it is above and beyond a linear effective time kept in the model. Otherwise, it's some smush together of linear and quadratic that doesn't really tell you anything. So just as we can have time and time squared on the mean side, we can have time and time squared on the variance side too. So we can have individual differences in each of these growth parameters. And they also take on conditional interpretations based on what is on the random side of the model. So in thinking about what's happening, it's like two sets of parameters are operating at once and they're doing different things. The fixed slopes are working together to describe what happens to the overall average trajectory. Is it going up? Is the rate at which it's going up speeding up or slowing down? The random effects come along and then say which aspects of this trajectory show individual differences. And so then if I have a random intercept, if there's no random slopes in the model, that's the random intercept that represents person mean differences. Once I put a random slope in the model, then it's person intercept differences at time 0 specifically. Likewise, once I add a random quadratic slope, so a random effect of time squared, then the random linear slope variance is conditional at time 0 as well. So individual differences in the slopes at time 0 specifically. So these numbers are going to move around as you add higher order terms, but it is an expected consequence of the fact that they change what they mean. If something goes from a lower order term or a higher order term to a lower order term, I should say. Want to see some equations? Said no one ever. But yeah, I want you to have seen these and to not be too afraid of them. Yeah, I know some people like the equations. You know, I used to think that subscripts were bullshit. I was like, who needs subscripts? Like, you're just like looking fancy and showing off. Like, no, subscripts are everything. And it took me learning these models to appreciate the beauty of a subscript, because it tells you what's a constant and what's a variable, and if it's a variable, what it varies over. It's complicated. So we are taking the model that you've seen before and we're adding to it to represent the idea of quadratic change. So YTI, Y at each occasion for each person, so T is my level 1 subscript, I is my level 2 subscript, is a function of 3 beta placeholders. So keep in mind, betas are not parameters. Betas hold sets of parameters that are conceptually linked together. So beta 0I is how each person is going to get their own intercept for their predicted outcome at time 0. That's going to be a function of fixed and random effects at level 2. Likewise, beta 1I is a variable that holds how each person is going to get their own linear time slope at time 0. And we're introducing beta 2I, another variable that holds how each person is going to get their own quadratic time slope, their own effective time squared at level 2. And E is still level 1 residual variance. E is the difference between where the model predicts your outcome to be based on your own curve. So each person is getting their own brand of bendy line here. And E is how far off each occasion outcome is from the bendy line predicted for them. That's a lot of lines, yes. You need at least 4 occasions to fit this model. Otherwise, with 3 occasions, there would be no E. The bendy line would fit each person's 3 points perfectly. Keep in mind, though, what's being estimated, though, is not a separate line per person, but variance across people. So we'll talk estimated parameters here in just a second. So because there are 3 beta placeholders in the level 1 model, there are 3 level 2 equations. So anytime you introduce a new predictor at level 1, it translates into a new equation at level 2, in which the slope of that level 1 predictor is a new outcome in the level 2 model. So I have 3 betas: intercept, linear slope, quadratic slope. Each of those then is partitioned or decomposed at the level 2 stage here. Okay, with me so far? So each of these is structured in the same way: fixed in red plus random in blue. Fixed is a parameter in the model for the means, a fixed intercept or a fixed slope. Blue is the idea that each person needs their own deviation from that fixed parameter. And what we end up estimating is the variance across people in the U0 intercepts, in the U1 linear slopes, and in the now U2 quadratic slopes. So 3 different kinds of variability at level 2. So then the interpretation of each: gamma 0, 0, that's my fixed intercept. Intercept is always my expected outcome when the predictors are 0. So in this model, that's when time 0 is. So it's the average predicted time 0 outcome based on this bendy trajectory that we've created. It's not going to be exactly what it is at time 0, but what the model bendy line says it should look like at time 0. U0 then is how far off my actual predicted outcome at time 0 is from the average for the model. So think about the trajectory that has been created for me and how discrepant my time 0 value on that trajectory is from the average one. So if I'm doing better than everybody else, my U0 is positive. If I'm doing worse than everybody else, my U0 is negative. Then beta 1. We've done this one before. One catch. Because of this time squared term, beta 1 is conditional. So everything in this line is conditional on time 0. So gamma 1, 0, what we used to call just the fixed linear time slope, that is the fixed linear time slope at time 0 specifically, because this model predicts that it changes as a function of when time is. Likewise, U1 is how far off my fixed linear time slope at time 0 is specifically to the fixed slope. So we put these together, we get to what your linear time slope at time 0 is. Put these two together, we get to what your intercept at time 0 is. Question: is there a gamma 1, 1, etc. for different times? Great question. So what happens in the level 2 equations is that the second subscript, the 0 here, is a counter for which predictor you're on at level 2. So I have gamma 1, 0. The 1 is because I'm predicting beta 1. So everything in this beta 1 line is going to start with a 1 because it ties to beta 1. The second subscript is either going to be a number, which indexes which fixed effect it is. So if I added a predictor in here, a level 2 predictor, a time invariant person characteristic, then its effect would be 1, 1. If I added another one in here, it would be 1, 2, 1, 3, 1, 4, and so on. That's coming in the next unit. I think we're a week or 2 away from that yet. And then if it's not a fixed effect, then the second place is a subscript for what unit of sampling the effect varies over. So these U's have an I subscript because they vary over people. Each person gets their own U0, gets their own U1. And then if I wanted to know the estimates at whatever time too, it'd request those as linear combinations. Ding, 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 ding. Yes, our friend estimate statements, lincom statements, and now contest 1D in R can give us predicted intercepts at any occasion as well as predicted linear time slopes at any occasion. And yes, I'm going to show you how to do that shortly. Last but not least, beta 2. Beta 2i is how each person gets their own effective time squared. Gamma 2o is the mean fixed effect for the sample, and U2 is how far off my deviation is from the fixed effect for the quadratic. So all the terms in this line start with the 2 because they're predicting beta 2. All the terms in this line start with a 1 because they're predicting beta 1. All the terms in this line start with the 0 because they're predicting beta 0. And you need 4 occasions to be able to estimate this. So if we add up everything on this page, how many parameters are in my model? Let's figure this out. We'll divide it up into the sides. So model for the means. How many fixed effects are in this model? Fixed intercepts or fixed slopes? Yeah, 3. How many things in red in general in my slides is what you can answer. Yes, 3. I have a fixed intercept, I have a fixed linear time slope, that's the rate of change at time 0, and I have a fixed quadratic time slope, which is half of the rate of acceleration. So I have to multiply it by 2 to talk about how it changes the rate of change. Now, how many parameters in the model for the variance? This is trickier. Let's count variances first. How many separate variances am I going to ask SAS to come up with? Okay, I'm seeing a variety of answers. Looking at the chat window. Oh, no one's typing. How many blue things? Yeah, 4. So there's 1 variance at level 1 because I have 1 E residual variance that right now I am saying is constant over time in people. So that's 1 number for the variance of all the E's. I have a second one is the variance of the U0s across people, a variance of the U1s across people, and a variance of the U2s across people. Said differently, this model predicts 3 different sources of person dependency. 3 reasons why occasions from the same person are correlated. Random intercept predicts constant person dependency, implies a constant correlation of the occasions from the same person. U1 and U2 each predict distinct patterns of non-constant correlation as a function of time and time squared. So we'll see more specifically what goes into those patterns in our example. Another question, okay, this is stupid, I doubt it. When is it called residual versus it's called not residual? Oh, that is actually not a stupid question, and this is me trying to save you all. So, to me, in my book and when I teach, I am very careful to say that this is U0 random intercept, this is U1 random slope, and this is U2 random quadratic slope. These are random effects. They have variances across people at level 2. I say that this is the level 1 E residual, which means within person variance at level 1. However, you will see other textbooks call these U's level 2 residuals. And so this is a level 1 residual and this is a level 2 residual. And I think that's just unfair. So I don't use the same term to mean 2 different things. So I say E is level 1 residual variance. These U's are level 2 random intercept and slope variances. I do say the lowest level is residual. So when they say residual for level 2, they're meaning residual in the sense of leftover. So like if you think about like when you first learned this distinction of what residual meant in the world of linear regression, you have a residual for the model that describes how far off your y that's predicted by the model y hat is from y. And then you have residual variance, which you learned as like variance left over. Technically speaking, in this model, this set of U's are not left over because they don't have any predictors yet. They are all of the possible random effect differences across people that there can be from the data. They are unconditional. Nothing is explaining why some people need higher intercepts than other people. Nothing is yet explaining why some people change faster at time 0, and nothing is explaining why some people accelerate and change more than others. These U's are unconditional. Once we get to the point where we have predictors in this model, then these become leftover U's in the same sense of residual as you were used to before. But I will call them leftover U's to try and be consistent with the terminology. Yeah, the terminology is a nightmare. It just totally is. I try to make it better to the extent that I can, but it's a nightmare. Point of the story, there's 4 kinds of variance in this model. That's where I was going with this. 4 different kinds. 3 of it is ways that people differ from each other. E is what is left over after controlling for the average pattern of change. So in thinking about what could predict each of these things, the type of variables that could reduce the random effect variances, the differences between people in their U0 intercepts, the differences between people in their U1 slopes, the differences between people in their U2 quadratic slopes. The only kind of variable that can reduce these U variances is going to be what? A level 2 between person kind of variable or a level 1 within person kind of variable? Which kind has the potential to go into this level 2 model and reduce these U variances? What do you think? Got 1 vote for between person. It's 50-50. So another vote for within person. Another vote for level 1. What can reduce the U variances here is the question. The answer is 2. So conceptually, U0, U1, and U2 are all the ways that people differ from each other in aspects of their growth trajectory. So if time 0 is at the beginning of my study, U0 represents initial differences. Why do some people start out higher than others? Well, I don't know. It has to be a person thing. Something about them, something that's constant to a person. Why do some people initially grow more? Why are they more, say, initially responsive to the intervention? I don't know, something about them. Why do they accelerate in their change more or slow down in their change more? I don't know, something about them. Functionally speaking, the level 2 model here is a between-person regression model. It's describing between-person differences in aspects of the trajectories, each of which you can predict with level 2 time-invariant person characteristics. So why did I start out higher than somebody else? I have a PhD. Why did I grow faster? I have a PhD. Why did I slow down more? I have a PhD. But if I go over here to E at level 1 is the discrepancy between the predicted growth curve for an individual and their actual outcome at each occasion. So what kind of variables could potentially explain level 1 E within person residual variance then? Between person things or within person things? Yeah, within. E conceptually is, why are you off your line today? I have a PhD. Not the answer. I had a PhD yesterday. I have a PhD today and I will have one tomorrow, because you know what? They can't take it back. That's the secret. It doesn't matter how shitty your dissertation is, they cannot take it back. It is now a part of you. So the fact that sometimes I can get through lecture without saying the wrong thing and sometimes I can't has nothing to do with a constant characteristic like my education level. It has everything to do with something that is varying within me. Whatever levels of concentration or enthusiasm or fatigue or frustration or anything that changes moment to moment, right? Those sorts of characteristics that are dynamic, that are measured at each occasion, those are the only things that have a shot at explaining E. Is there a way to be both a within person and a between person thing? Oh, yes. Yes, there is. So let's say that you had something like a perceived level of stress, and you measure perceived level of stress at each occasion. That is a perfect example of a predictor that can be both a between person thing and a within person thing. Some people perceive more stress than other people. Period. Whether they have it or not, I'm not going to go there, but the variable I'm playing with here is perceived stress. Some people perceive more stress than other people. Some occasions are worse than others. So the extent to which your stress level is elevated relative to your own baseline, that's the within person part. The extent to which you, on average, perceive more stress than other people is the between person part. And what's going to happen when we get to level 1 predictors is that we literally have to carve them up into the 2 separate constructs that are buried within them. We will have 2 different versions of the predictors, and that is why Kelly's life is going to be a nightmare in the project that she's working with, which is a 4-level model. Because every variable measured at level 1 is 4 things. So back to this model. There's 4 kinds of variance in here. How many covariances are there in this model? Because that's not on the slide. When we add random slopes, we add their covariances with the variables, the random effects that are already there. How many covariances are in my model? Got a couple votes for 3. 3 is correct, because you only have covariances among the terms at the same level. So U0 has a covariance with U1, U1 has a covariance with U2, and U0 has a covariance with U2. So there's 3 covariances among the U's. By definition, there are no covariances between U's and E's. Random variables at separate levels do not relate to each other, ever. So we've got this model queued up here. We said there were 3 fixed effects. We said there were 4 variances, and we said there are 3 covariances. That's a total of 10 parameters that I'm dealing with here, right? Counting them all up. Now, conceptually, how many predictor variables are in my model? How many predictors are in my model, conceptually? 1. 1 predictor, and I've made 10 parameters out of it. 1. These things get real ugly real quick. And at this point, usually someone raises their hand and says, but in all of my models, I have to control for like 20 variables. Are you telling me that I'm going to have 200 parameters? Yes. You could have that many. Yeah. Generally speaking, things are exponentially more complicated in these models because of the potential for different effects at different levels for lower level predictors, and because of the potential for not only fixed effects, but random effects as well. So yeah, it can get real ugly real quick. But that's what you have me for. I try to make it less ugly. All right, what's the next slide? Oh yeah, orders. So here's the process by which I would recommend going through step by step to see sort of what level you need to maintain in terms of your complexity. So we did this in example 6, started with empty means random intercept. Then we do fixed linear time slope. We can directly check the p-value that shows up for it because it's a fixed effect. If we then add a random linear time slope, meaning we keep the fixed time slope and we add random, then we do a likelihood ratio test because we would have added a random slope variance and its covariance with the intercept. We could then examine the fixed quadratic slope, check its p-value for whether it's significant as a fixed effect, and then you could do random quadratic. And that would be a likelihood ratio test to see if you need that new slope variance plus the 2 covariances that came with it. And you could keep going in order. If you're like, I don't want to estimate 5 different models, I'll show you how to cheat. You know the cheaty way to get this done faster? Start with number 5. If you start with the most complex model and try to back it down, so if you start with random quadratic and remove the random time slope and fit gets worse, you're done. Because you know you need everything else underneath it to support it. Let me do something real quick here. I have an idea. This is the part where in normal life I would have written on the board at some point, but we're not in normal life. We're in Zoom land, but I can still write on the board. So let me do a little live demo here. Terms, hierarchies, what things mean. So if I have the mean side, means model, variance model. So I can have, say, a fixed intercept here. I can have a random intercept here. What would I call this? If I have a fixed intercept on the mean side and I have a random intercept on the variance side. Yeah, empty means, comma, random intercept model is what I would call this. So next step would be fixed linear. I would call that fixed linear time, comma, random intercept, because I have different levels of complexity on each side, and so I'd have to keep that separated. If I added random linear time, then there are simultaneously 2 sets of hierarchies happening. On each side, if I have a linear effective time, I need to have an intercept underneath it. Likewise, if I have a random linear effective time, I need a random intercept underneath it. Across sides, random trumps fixed. So if I have random linear time, that automatically means I have to keep fixed linear time with it, because random linear time is adding the u that deviates from the fixed effect. So what it's deviating from, the fixed effect, has to stay in the model. So if I have this term right here, random linear, I call that a random linear time model, and it is implied that all 3 of these other terms are also included. So then if we add fixed quadratic, I'd call that fixed quadratic, comma, random linear, because I'm differentiating the order of complexity on each side. And if I add random quadratic, same sets of 2 hierarchies apply. Because I have fixed quadratic on the mean side, I gotta have fixed linear time. So if I have time squared, it's only interpreted as a quadratic if I also have the linear effective time. Likewise, on the variance side, if I have random quadratic, I gotta have random linear underneath it. Going across the 2 sides, I have to have fixed quadratic if I have random quadratic, because random quadratic is adding a u that deviates from the fixed. So then just saying that the model is this, I have a random quadratic time model, that one phrase covers all 6 of these things. So what if I had this? What would I call this? Not a model. Yeah, I call it wrong. That's what I'd call it. Now, what's wrong with this? What I'd be saying is that I have individual differences in change, but I have no average change. Individual differences from a zero line. So even if fixed linear is not significant, I keep it in the model. Now, what about this? Can I do this? 1 vote for yes, 2 votes for yes. What do I call it? Yeah, fixed quadratic, random intercept. Conceptually, what kind of trajectory would this look like if this is what fits best? The same change for everyone, but they start in a different spot? Yeah. I'd go with parallel bendy lines. Fixed quadratic means there is some curvature to the line, so there is acceleration or deceleration, but the fact that people don't need their own time slope or time squared slopes means that the change is the same across people. So parallel bendy lines is what would be implied by this model. Likewise, if we had something like this, this is also acceptable. What it would mean is that there is curvature to the line, but it's the same degree of curvature for everybody. So people slow down or speed up the same. And so this is where the program that I wrote in SAS to simulate these sorts of models, you can play with the values to see what the trajectories would actually look like, and that might be helpful in conceptualizing how you can get across these. All right, how are we doing? Ish. Let's see, what's the next? Ah, yes, okay. We'll do just a couple more and then that'll be it for today. So back to PowerPoint here, slide 19. So this is just reminding you that the same conditionality with respect to what becomes conditional on time 0 that we saw on the fixed side happens on the random side. So on the random side of the model, regardless of what's on the fixed side, as you add terms sequentially as new random effects, if I only have a random intercept, then that intercept variance represents between person differences in the mean. It means the lines are parallel. So people start out at a different point and they stay just as far apart as time goes on. So this implies that people differ from each other in only one way. There's only one source of person dependency. It is a compound symmetry, constant variance, constant covariance kind of model. It is repeated measures ANOVA, functionally speaking, in terms of what is predicted on the variance side. If I add a random linear time slope, then the intercept is no longer referring to between person differences in the mean. It's between person differences at time 0 specifically, because what happens is that different slopes imply people spread out. So the U that you would have at the ending occasion is different than the U that you would have at the beginning. If the random linear time slope is the highest order term in the model, then it has the variance in the linear rate of change, period. Unconditional. There's only one number. If I add random quadratic time, the random intercept is still individual differences in the intercept at time 0, although it's predicted based on a different model. Now the random linear time slope becomes conditional. It becomes individual time slope differences at time 0 specifically. So it will be a different number because it means something different. And random quadratic time slope variance then is individual differences in half the rate of acceleration, which is constant across time. So you'll see the piles of variance shuffle around as you add things to the model because they change what they mean in the same way that the fixed effects change what they mean. And how many can you have? So here's an explanation as to how many occasions you need to estimate different types of models. So if I have 2 occasions, first row here, let's say I've got pre-test, post-test, the end. Then in terms of pieces of information going in, I have a variance at time 1, I have a variance at time 2, and I have a covariance. 3 degrees of freedom, so to speak, 3 pieces of information. I can try to predict that with a random intercept and a residual variance. And at most, I could say that there's a different residual variance in the R matrix at pretest than at posttest. If I did that, I would spend all 3 parameters. I can't have a random slope. If I added a random slope here, I'd have to get rid of E in the R matrix. I'd be saying that the only source of variance is between person slopes and that there's no residual, and that's unrealistic. If I have 3 occasions, now I have 3 variances going in, I've got 3 covariances going in. I can try to represent that with a random intercept in G, 1 random slope related to time, and its covariance. I spend 3 parameters there, and if I have a diagonal R matrix, E variance is the same in each occasion, that's 4. If I tried to add a second random slope, I'd have to cancel E. If I have 4 pieces of 4 occasions, then I have 4 variances, 6 covariances, then I can have 2 random slopes with respect to time. So that could be linear and quadratic time. That could be 2 different slopes for different sections of time. We'll talk about those piecewise models. And then 1E, so that's 7 degrees of freedom. So SAS will tell you when you've overspent. It will end up with a table that's called covariance parameters at last iteration. That's what it will say. Like, I gave up, here's the best I could do. And you won't get a full set of results. So if you try to estimate more than what is possible, then with this rule, you will find out the hard way it's not possible. Okay. Yeah. This is a great place to leave off of. This is what the model says the predicted variance should be at each occasion from a random quadratic model. Right here. This ugly thing right here. That's how a random quadratic model patterns the V matrix. It is a function of time to the 4th power. And here, down here, is how the random quadratic time model predicts the covariance between any pair of occasions, which is also very ugly. So this is to say, when you add random quadratic time slopes, you're creating a distinct pattern of total variance and covariance that's related to time. It has extra higher order terms in it relative to linear. It's an empirical question as to whether this creates a pattern that matches that of the data. That's what we would still have to go and figure out. We went over this slide already. One more. Correlation between intercepts and slopes. So the idea of estimating covariances between random effects is something that some folks think is debatable, and I am not one of those folks. But I think it should always be there. If you have a random intercept and you have random time slopes, if they come from the same person, they should have a covariance, the end. That's what type equals UN on the random statement does, or cov type unstructured in Stata, and what happens in Elmer by default. But what that covariance means depends on time 0. So if I have a function that looks like this, if I take the intercept at this point, where people pretty much have the same predicted value, there would be 0 correlation between their predicted value at this point and their subsequent rate of change. If I put time 0 back here, now I have a perfect negative correlation because people who are the highest at this occasion grow the slowest. What if I put time 0 over here? Now I have a perfect positive correlation because people who are the lowest grow the slowest. all three of these correlations accurately describe the same data. So this is to say, if you're interested in interpreting the correlations between your random effects, you can do so. Just be super duper careful to remember what they refer to. Are they the mean over time for the intercept, or time zero, or something else? Time zero is what the intercept correlation refers to. So whether that's the beginning or the end depends on how you coded it. But non-parallel lines will eventually cross. Likewise, correlations among the linear and quadratic slopes are likely to be dictated by your centering as well. So if you look at just these columns of numbers, for instance right here, linear time and quadratic time, do you think those two predictor variables are going to be related to each other? Linear time as a predictor and quadratic time as a predictor? Yeah, I think they might have something in common. So here's a positive relationship between those. Now, what if I do it this way? What if I center time at the end? Now I've induced a negative relationship between these numbers. Only when I do mean centering for time have I eliminated the correlation between linear and quadratic time slopes. So for that reason, some statisticians recommend mean centering time if you're going to fit these models, because then the linear and quadratic the correlation between the linear and quadratic random slopes will be at a minimum. However, when is time zero in this ladder coding scheme? Time 3.5 that I don't have. So that means all of my references to time zero in the model, my fixed intercept, my random intercept, and all the main effects of my predictors are going to refer to a middle occasion I don't actually have. I find that dissatisfying. So this is to say, tread carefully in interpreting correlations between linear and quadratic time slopes, because they are going to be heavily influenced by how you've coded time. The end. There. See, look, we made it to intermediate summary. And we'll get to the SAS code that goes with this next time. So, questions before we call it a day? No, we're ready to call it a day. I hear you. So have a good Tuesday. I hope to see you in a few days. Office hours start now. Let me know if you need anything.